Yeah, so I'm really happy today to talk to you about stellar halos, and especially stellar halos beyond the Milky Way, and what some of the upcoming future surveys actually coming really fast might be able to give us. And part of this talk is also going to be a call to action, because we need to have a better theoretical understanding to actually get the information out of all the wonderful data that these surveys are going to give us, and learn about how galaxies form and evolve. So I'm a research assistant professor at Northwestern University in Scheira, and I'm also part of the new AI Institute for the Sky called Sky, which is at Northwestern, U Chicago, and University of Illinois Urbana-Champaign, and which just started last month. And so actually what I wanted to flash first is that we will be hiring, and there are postdoctoral positions and associate fellowships and preceptor positions, which are part research, part teaching. And so if any of that interests you, feel free to reach out. And the Sky Institute is actually going to be in this building, and I think we're going to get the 34th floor. Yeah. It's been really nice. It's really nice to be here and to talk to you about stellar halos today, because for me, it brings together a lot of the things that started when I was here at the CCA. And that is because my interests are in galaxy evolution, but in combining effects that are more external in mergers and environmental impacts, and internal physical processes that go about the star formation and any feedback from star formation or quenching inside of the galaxies. And so when I was at the CCA, it was very early days. The CCA was a lot smaller, but there was the galaxy formation group was starting, and actually the galaxy dynamics group was also starting. And so it was great to be able to great and challenging to actually go back and forth and go learn a lot from people in both groups and combine some of the information. And that basically I've carried on forward, I hope, and combined more and more a little bit the things I learned from both. So if we look at the larger scale structure of the universe, we see the nice cosmic web, in which dark matter halos form, gas falls in, galaxies form, and things keep accreting, and galaxies actually interact with each other, which has a lot of environmental influence in galaxies. On the other hand, if we look at individual galaxies, we often think about the physical processes that go on inside of these galaxies, which is the gas accretion, but more the cooling and the heating, the inflows and the outflows within the galaxies, the ISM and the CGM, the star formation and stellar feedback processes, small scale physical and chemical processes that involve gas, dust, and radiation, supermassive black holes, of course, the feeding and the feedback of these. There are secondary dynamical processes that involve the disk and the bars, bulge formation. And then because of feedback, actually locally and globally, there can be a quenching of star formation, which can be partially external or internal, or a combination of both. And so what I am interested in is, can we untangle these effects that are internal and external, and see what processes form some of the features that we see in galaxies in our universe, and use what we see to better understand the underlying processes. And that these external, it's very simply said, like dividing it up in external and internal physical processes in galaxies, but that these interact. It's actually very clear from our local environment. In just to give one example, in our own Milky Way, if you look at the star formation history, then there is a relatively, well, not recent, but a peak about 6 gigayears ago, which seems to coincide possibly with the infall of the Sagittarius dwarf galaxy. And similarly, people have argued that M31 probably had a significant merger about 2 gigayears ago, which shows up in M31's stellar halo in having relatively metal-rich stars in the stellar halo, a giant feature, a giant stellar stream in the halo, structural kinematical tracers in that stellar halo, but also a global burst of star formation in the disk of M31. And there is, in that case, a compact and metal-rich satellite, which could have been the satellite in the merger. And so here, both of these internal and external physical effects show up in the history of the star formation of the galaxy, but also in the extended features, the extended outskirts of the galaxy itself that we call the stellar halo. And stellar halos are a function of hierarchical structure formation, and simulations have found that these form in almost basically all galaxies have some form of large-scale features, low density, low surface brightness, large-scale features, and simulations have found that consistently over many, many years. And yeah, these are just to show you some examples from different kinds of simulations at different scales. But so what can we learn from these large features? So stellar halos, and here this actually shows the stellar halo of M31 from the Panda survey, where you can see the giant stellar stream that I mentioned, and here's the disk of M31. But you also see a lot of other substructures. So stellar halos, because they form in this hierarchical process, provide clues to a galaxy's past evolution. And because it's smaller galaxies that fall in and get disrupted into this larger system, they actually also provide clues to how low mass galaxies form. A lot of the information that we have on how dwarf galaxies form and evolve is from Milky Way satellites, and sometimes even from disrupted Milky Way satellites. But secondly, extended features like streams and shells, they trace the host dark matter potential, and they provide us constraints on dark matter halo shapes, the sizes, and any additional substructure that might be there in the potential. And in our own to show you a few examples of that we see a lot of these in the nearby universe. This is just a small sample of the Large Stellar Stream Legacy survey that shows very nicely these features around many, many galaxies. And if you just look at the frequency of how often you would see these, then up to the depth that can be reached in these kind of ground-based surveys, the simulations and observations seem to largely agree in how many observable features you would have. However, if we want to go deeper and actually see some of the fainter structure and some of the faint smooth halo that is built up out of a lot of smaller accreted structures, we have to go very, very deep, which is more challenging to do. And so this is one example of where people have gone to for ground-based imaging pretty deep images going to around 31st magnitude surface brightness. And then you start to see that almost all of these galaxies have extended structure around them. And you can also see more and more substructure arising. So to see these, we really need to go deeper. There are many around our own Milky Way. We have seen many stellar streams, thin stellar streams that are from probably from globular clusters, disrupted globular clusters, thicker stellar streams that are probably from dwarf galaxies, streams where we are not completely sure what their origin is. And this started with just seeing some structures in SDSS survey, but also now we know, I think it's getting close to 100 or maybe by now it's over 100 streams in the Milky Way. And the advantage of having these in the Milky Way is that we can get a lot of additional information and where we can learn a lot. We can look at them in very different spaces, especially with the with Gaia. We've been able to look at them in different velocity spaces. With spectroscopic follow-up, we can get mentallicities. We can look at in orbital spaces and energy and angular momentum, and all of these give us different information. And that has allowed people, and among which many people here in the room, to learn a lot about the accretion history of the Milky Way and the environment of the Milky Way itself. But if we want to go further out to other galaxies, then this is challenging. And there are ongoing surveys that try to do some of this. For example, looking at Milky Way systems with satellites, so such as Saga and ELVS. The Stellar Stream Legacy Server, where I showed a few examples that focuses on dwarf galaxy stellar streams in larger galaxies. The lights where I showed an example of looked at faint stellar halos, and these are also mostly focusing on satellites. However, in the coming years, we have and actually already, because Euclid's up there, we have a few large surveys coming up that will allow us to do this for many more systems. And so that's mostly what I want to talk about today, and what I think we can do with the theoretical tools that we have now and that we need to improve on to actually learn from that space. So to give you a little bit of details, and I hope I got the numbers right. They're sometimes hard to find. So Euclid launched. It's up there, and if you look at the early release data, it's pretty amazing. For example, they found for a Milky Way globular cluster, how the globular cluster actually deforms in the tidal field of the Milky Way. And they've already found many new dwarf galaxies, many new globular clusters. Euclid's going to do a wide survey up in the visible up to about 29th magnitude in surface brightness, and the resolution is pretty good. Rubin, wait, it has not launched. It's gonna start very soon though. So we need to absolutely get ready for that. It's gonna do a large part of the sky, so it's a very wide survey. And in the 10 years that is planned for Rubin, estimates are that you will get to about 30th magnitude. So it's kind of similar actually, at poorer resolution though. The Roman is the current launch date is late 2026. It's a smaller survey. It's still a wide area survey. If you think about the high latitude wide area survey, which is most applicable to the science, it's going to be deeper than the other two. and the resolution is going to be significantly better as well. And so the main thing that I wanted to put up here is that the area is different. So the number of galaxies you would expect is different, but also Euclid and Roman are going to be able to do the nearby universe in resolved stars. Rubin is going to be not as good for that, but it's going to be great in integrated light. And so there are opportunities in all of these that are slightly different, but that all give you slightly different information, which is great. And I mentioned this because I'm jumping a little bit back and forth between these instruments and between prospects for these instruments in the talk. So for example, for Rubin, people have made synthetic images, and these are some examples of tidal tails and stellar streams and shells that you might see in Rubin images. And actually, there's been quite some work. People have already been quite some preparatory work in how are you going to classify galaxies, classify whether things are mergers, and try to classify any stellar halo features that you see. And that's actually a challenging thing because a tidal tail is going to look pretty similar to a stream in some cases. There are key challenges here, and that is detecting the faintest features. The standard observational pipelines are not optimized for large, smooth structures in the sky. And there are some efforts to improve that, but we may want to do a whole new setup to actually go and try to target the faintest features over larger areas of sky that are very different than finding the individual galaxies that are the brighter, smaller points or individual stars. And secondly, where the theory comes in, the interpretation of the detected stellar halos is still very, very hard. If you're going to see a lot of these, what does it tell you? There's a lot of information there on the past history of these galaxies, but how are you going to get it out? And how are you going to get it out if you don't have kinematics, if you don't have any chemical information? Maybe you have colors, maybe. And what is the statistical power? We're going to see this for many, many galaxies. What is the statistical power that is there and that we can really fold into our models? So in some of these, I look forward to working with my colleagues in AI in this new institute. For example, they have ideas on how to go to fainter features, how to, for example, assign light in individual pixels that can come from multiple sources, how to do this in a probabilistic sense. And so I'm excited to think about that, even though I'm not an observer. Yeah, and on this side, we need to think more about the simulations, accelerate the simulations, build tools to do inference on large faint features. And I think that's a challenge in itself. Okay. So to talk about theoretical predictions, there are many, many ways of doing theoretical predictions, and they all have their own power. They also all have their own downsides. And I'd like to talk you to a few of them. So we've seen some of the cosmological large-scale simulations of galaxies and forward modeling these to synthetic observations where you get a large sample of galaxies. And you can see how some of this evolves in the cosmological environment. We can do this for higher resolution zoom-in simulations where we have better resolution and we have a better sense of, we can resolve the dwarfs, we can resolve the satellites, and it can even resolve streams. But this is often restricted to a few galaxies. On the other side, there is the dynamical modeling in isolation, where you look at, for example, individual structures, and which can be very, very flexible. And you can explore many different galaxy potential models and different properties of your streams. And this can be very high resolution, but it's individual systems. And I want to give you an example of that. So actually here at the CCA, Sarah Pearson and I looked at whether you would be able to observe globular cluster stellar streams in Roman in external galaxies, and up to how far. And so to do that, we took observations from the PANDA survey from M31, fitted isochrones to that, and projected what they would look like in Roman, and added streams. Actually, we added 3 streams. They're in here. And so with the current limits of the PANDAS data, you maybe see 1. If we go to Roman, this is what you would see. So Roman will resolve most stellar streams. And this is actually, we find this is likely to be true out to about 3.5 megaparsecs, where you will resolve the streams with respect to the background density of the stellar halo in individual stars. And this volume contains about 200 galaxies, although they're mostly dwarf galaxies. So in the Milky Way, people have found a lot of substructure. Actually, the better we know the streams, the better we look at the streams, the more weird features we find, which is awesome. And which tells us a lot, is just figuring out what it is. But one of the things is gaps that might be created by dark matter halo substructures colliding with the streams, basically. So this can be an indirect detection of dark matter models, and it can actually, because they're at the mass range where dark matter models diverge, this can actually be a very interesting constraint on dark matter models. But there are other things that can create substructure and gaps and overdensities and underdensities in streams as well. And so we need a larger sample. We need to get statistical power to actually be able to do some inference in multiple galaxies. And so the next question we asked is, will we be able to detect substructures such as gaps in these extragalactic streams? And Christian Aganse, who is now a postdoc at Stanford, a fellow at Stanford, looked at this and did a similar setup where he created a stream with a gap, put it in an M31-like stellar background halo, and projected it out. And so we find by both visual inspection and actually automatically doing a gap finder technique, that you're likely to be able to detect gaps in stellar streams out to 2 megaparsecs. If you know where the stream is, you can likely find the gap. So another thing that's found in the Milky Way is that stellar streams are influenced by the infall of the LMC. And this is an illustration of one of the first papers that talks about this, where the kinematics of the stars in the stream do not align with what you would expect given the stream track. And there's been a number of works looking at this, and there's actually been recent work by a CCA pre-doc, Richard Brooks, very nicely looked at many streams and how these are affected by the LMC. And so we did a somewhat similar but different approach in asking, well, if we think about other galaxies, don't have the Milky Way history, then they will have ongoing mergers. So what actually happens with the stellar stream if you have an ongoing merger? And so we used a large sample of streams in a live and body simulation we carefully picked out ranges of orbital properties, and we simulated them in high resolution in a merger simulation, and systematically also changed the merger parameters. And so I have a movie that shows you just a few of the streams and the merger coming in. So on this side, we have an isolated Milky Way. On that side, we have a Milky Way that is fully merging with, in this case, a 1-to-5 merger. And so you see that a number of the streams have very different evolutions. They get pulled out. They move around. Some of them are very disturbed. Some of them you might think would not be visible anymore, but others still survive, but get on very different orbits. And so we can look at this for the whole sample. So if you look at the streams that are in the inner part of the galaxy, that are nicely thin streams in initial conditions, nicely thin streams, but longer if you evolve them in isolation. But in a merger case, get messed up significantly. Although there are also still streams that survive. If you look at the streams that are more in the outer parts of the halo, they grow as well, stay thin and nice in isolation, even though this is there's no spurious heating in the embodied simulation. But in a 1-to-5 merger case, the streams move all over the place, and they can actually move out much further. They can also move in a lot. And so to see what actually causes this is that there is some trend with the initial orbit of the stream and initial orbit of the satellite, but the key is whether a part of the stream encounters the satellite within a short distance. So here we've quantified a change in the orbital plane of the stream, and this can be up to a complete flip of the orbital direction, and a change in the thickness of the stream, which can also be very significant, against the minimal distance of the stream and satellite over the first part of the merger. So the first two pericenters, basically. And you see that it goes up significantly at a distance of about 20 kpc. If we look at different mass ratio mergers, and we look at the changes in energy that we see in streams, then there is a clear correlation where statistically you have a sense of how big the energy changes can be, and this correlates with how big the satellite is that comes in, or how big the perturber is that comes in. So for a large perturber, the change in energy is significant. For a 1 to 100 perturber, there's still some, but it's much, much smaller. And to show you an example of one stream where this shows you coordinates along the stream track. So a nice stream is just a straight line basically here, and X, Y, and XZ, and the right panel shows you the orbit of the stream. And in the top panels in the merger case, you see that this stream is it basically gets destroyed, but it gets destroyed in a way that it looks still cohesive in positional space, but the orbits of all the stream stars is very, very different. And so there's no single orbital plane anymore. And every star just orbits on its own radial motion. Okay, so we can try to input that to understand what we would expect for the existence of globular cluster stellar streams in other halos that have had different merger histories than the Milky Way. And to talk about other tools, there's a big space here open. So you can do hydrodynamic galaxy formation simulations. You can do high resolution body or massless test particle simulations. Although in this case, it's also n-body. But there's still a lot of space in between. And I think that space is actually really interesting to explore the physical parameter space and get statistical samples. And that space is covered by empirical models and semi-analytic models. And I'll briefly, in this case, I'll show you a few examples of how changing the physics in these kind of models can get you very different outcomes in the stellar halo. So in the first case, this is work that I did with Martin Ray, who's at Oxford. And we looked at the merger history and diversity of stellar halos. And what we did is base it on a cosmological dark matter only simulation, zoom in simulation of a fixed galaxy, fit an empirical star formation history model to it, and then particle tagging onto the dark matter only simulation. However, we enhanced the dark matter only simulation by slightly changing the initial conditions that would not change the final properties of the halo, but only change the accretion history. So when do the major mergers happen and how big are they? And this is called genetic modification of your initial conditions. And so if we do that and then follow the same procedure, we can find where our star particles are in the stellar halos at the end. And we find that we get very, very different stellar halos for the same galaxy in the end. And so, for example, here we show two sets of galaxies where we modified the initial conditions. And what this shows is the total stellar mass of the system and the stellar mass that is roughly in the stellar halo, that is outside of the inner 20 kpc of the galaxy. And you can see that variations, you can get smaller stellar halo masses or actually turn around. But you can get up to order of magnitude different stellar halo masses by just changing when the mergers happen and how massive their accretion, the mergers in the accretion history are. And so because we did an empirical model, another thing that we can change pretty easily is how much stars you expect there to be in stellar halos, how much stars you would expect there to form in the form of the stellar mass halo mass relation. And so we changed the slope of that relation, like what's the stellar mass per halo mass, in different ways, following models that people put out in the literature, and then looked again at how much mass would you have in the stellar halo, and you see that not only is the stellar mass different, but also the spread within the sample is different. So it's not just that the total stellar mass that you would have, that you would see in a stellar halo, is an effect of a galaxy's accretion history and of its formation physics. But statistically, if you look at the larger sample, this suggests that actually the spread in that sample tells you something about the underlying physics. And actually, to show you how different galaxies can be in different accretion histories, so these same galaxies have been run with hydro as well. And you can see that not only is the stellar halo totally different, but even the galaxies themselves look very, very different. Even if you have the same mass accreted, it's the timing and how much mass at which point gets added to the galaxy, which can totally change the appearance of the galaxy itself and its environment.
These are still like idealized simulations where you're just throwing.
These are cosmological zoom-ins.
These are cosmological.
Yeah. So another way we can play with basically the same thing, and in this case, I'm on purpose playing with the same thing, on purpose playing with a stellar mass halo mass relation again. But in this case, this is a semi-analytic model that's built on the centigrade semi-analytic model, but to follow the disruption and evolution of satellites and substructure in stellar halos and how those phase mix and then build up the smooth stellar halo. And so how to read this plot is that over time, if you go from the beginning of the universe to now, if you look at an average, in this case, it's an average LMC-like galaxy, the satellites fell in, which is the blue line, and some satellites are in radial orbits. They get disrupted very quickly. They form shells, but satellites fall in, they get disrupted at some point, and then they form streams, and then slowly those streams get disrupted, and everything phase mix and forms in a more smooth component. And so we can follow that evolution through the model, and then we can make predictions for what you would be able to see in these future instruments. And because we're using here the power of the semi-analytic model to do a large sample and to sample a large range of accretion histories, we can make a statistical prediction in the sense of what's the likelihood that you would observe a certain number of streams with Euclid, Rubin, or Roman. And so I tried to put in the lines that are the expected depth that you would get. But in all of these systems, in the default case, you would expect you would expect in about 30 to 40% of LMC-sized galaxies to find some kind of substructure in all of these surveys. However, if we now change the physics again, and we change how the stellar mass halo mass relation is, and we steepen it, and in this case, it's a significant steeper form, then we get a totally different outcome. And so again, we can use these tools to make predictions under different physical assumptions, basically, and see how this comes out, and then invert that, use the observations, and actually the large range of observations that we will have to learn about the physics. And so adding these two in, I think there is, to really understand how a stellar halo is built up, what it tells us about the galaxy, and ideally also use the information of the galaxy itself to learn about its history. We need to use the information that we get from the large-scale cosmological simulations that give us many galaxies, but not a detailed resolution to look at individual substructure. The higher resolution simulations that give us some individual substructure. In this case, it will give us, it can show you the dwarf galaxy streams, but not the globular cluster streams. Then with semi-analytic models, we can test out theories and get statistical samples again, but there are limitations in the spatial information that you have. And with high resolution dynamical modeling, we can follow individual cases. We can do a detailed study of the physics that affects substructure in individual cases. And then we can make the step of, for example, folding in what happens with features during the merger back into our semi-analytical model to make those predictions tighter and to improve those predictions and improve the inference that we can do. And as a last step, I wanted to show one teaser of work in progress that's very, very preliminary. And we know there are still issues with it, where we're actually working in these high resolution zoom in cosmological simulations to model the formation of stellar streams from detailed globular cluster evolution simulations. And so this is built on work that Mike Rudge's been involved in to find the places where globular clusters form in cosmological simulation, high resolution cosmological simulations of galaxy formation. Then to export the properties of that and the evolving tidal field of that area to a separate cluster evolution simulation that does all the internal dynamics of the cluster and predicts what the escape fraction of and the escaping stars, actually the individual properties of all the escaping stars are. Then we're putting that back into the cosmological simulation and following the escaping stars in the evolving galactic tidal field. And so this is some early results of the most recent results of doing that last step, taking the escaping stars from the globular cluster over time in the evolving potential of the galaxy and seeing where the stars end up. And there are still issues with this, so the appearance may change, but how it looks now is that the older part of the streams actually get partially disrupted and they form almost separate streams. And only the most recent part of the stream is continuous and will be easily visible as one continuous stream. And the color coding here is just by age. So there's no, it's not density, it's just when things get stripped. But we'll see if that holds up when we improve the models. And yeah, I should say, this movie is made by non-Pani Paisal, who is at Carnegie, and the team working on this is Robin Sanderson, Carl Rodriguez, Sarah Pearson, Mike Rudge, and Brian Cook. And it's been a lot of fun. And so I wanted to, again, flash position advertisement. There's also postdoc positions, postdoc fellowships at Sierra itself. So if you want to hear more about that, ask me as well. But I think that deadline is in a few days. And then as a concluding slide, I wanted to leave you with this. Thank you.
I saw a tentative hand. No. Just moving.
So wonderful talk.
Can you use the microphone?
Oh, sorry.
Okay.
Wonderful talk as always. For the SAM plus predictions for surveys, can you make predictions for something existing like SDSS and see whether it roughly lines up with what you expect?
Yes, I should be. Yeah, my aim is to first get the methods paper out, but yeah, that'd be great. Yeah.
guess while you're thinking, I'll ask. I wrote too many questions down. Let's see. So one question, and actually it's my one too. I think that people have been thinking about extragalactic streams for a while and what to do with them. And I think it's still a big open question, but I think even in the best case scenarios, people assumed you'd be able to like extract individual streams and then cram it through your pipeline that does some inference about the dark matter or the galaxy or whatever. But it doesn't seem like that's really going to work, right? Like they're all overlapping. You can't really distinguish whether one stream or feature over here is connected to another one.
Yes.
What do you think the future is when you relax that assumption?
Actually, Danny and I talked about this today as well. I think the future is you need to model the whole thing and you need to do inference on the whole thing. Because if you try to do individual features, the first question you have to ask is it really a stream or not? Is it a tidal tail? Is it a shell? Do you see everything that there is? Even in the Milky Way, we probably don't see the full stream. And
so when you say everything, you mean the galaxy and...
Well, ideally, yes, the galaxy as well. But even if you just look at the stellar distribution outside of a star forming disk, I think the best way forward, and especially to deal with all of this information, is you want to do some concerted model of the whole accretion history, how that builds up the substructure and the smooth halo, and then fit that. And I do think we have all the pieces to do it. It's just putting them together in the right way. And we have the statistical pipeline to do it. Yeah. I think that's it.
For a postdoc at Sierra. Carrie and then Richard.
Hi, it's just super exciting to think about the future, but what are the implications of not finding all of the stars that belong to a cluster? Like you showed that really cool example of, we're missing some of the Milky Way stars probably, or Milky Way cluster stars. So what part of your inference does that mess up?
You need to include that in your forward model.
Okay, cool.
Yeah, and I think even for streams in the Milky Way, it's like I think the theory and the observations are good enough that it's worth starting to think about that.
Okay.
It's like, what are the stars that you see? You don't see all the stellar types.
Yeah, so trying to find the stuff that we're missing.
And trying to understand how we expect the full stream to look like and what you would actually see, I think is something that we can do. Yeah, and there's a little bit in the literature about it. Yeah.
Really nice talk, Tjitske. Thank you. So, I mean, it seems clear from what you presented that what we're going to see is a mishmash of stripped galaxies and stripped globular clusters, right, at the end of the day. And so that also seems very challenging to disentangle. What I'm wondering is, I've been so struck by the power of having the metallicities in the Milky Way, right? So you kind of touched on this, but what are the prospects, for example, with ELTs of getting metallicities, maybe not for individual stars, but like at least for some of these integrated structures? Is that going to be within reach?
For a nearby universe, yes. Actually, Roman has a GRISM, which would be great. Also, just having, it's like some of these surveys are still being defined. And so how much of a color, like almost equal depth in color and different colors you're going to get, in different bands you're going to get, so you can get some color information, would also help. The challenge is that often these stellar halos are mostly old, but they're not consistently old. And there might be interesting things in that relatively younger systems that just fall in might have a very clear signature actually in color. I am less worried about the dwarf galaxy versus globular cluster, just because the dynamical coldness of the streams is very different than we would expect. And it's also, you're going to see, yes, you're going to see a mismatch, or you're going to see a mishmash. It's so messy. It's going to be messy, both in the nearby universe and resolved stars, where we could be able to observe the globular cluster streams, and in integrated light further out that we could see with Rubin. But I'm more hopeful in disentangling actually the globular clusters from the dwarf galaxy streams up to some point. There's always going to be some boundary cases, but in general, I think, yes, that's not going to be the main thing.
Lovely stuff, Tjitske. Class talk. I'm wondering, so you talked a lot about like the streams and the shells and the prominent structure that you can see, right? But we also know that there's like a lot of facing things that may not belong to us, which you should also be able to see far out in the stellar halo, where we don't really necessarily see that in the Milky Way. What are your thoughts on that? Like, what can we learn from that?
I think we can learn a lot from that. And actually, the things that you will see in the substructure are the things that either are massive, were massive, or fell in relatively recently. And so actually the smooth component is going to tell you about all of the small things that came in. And so coming back to this, the different shapes of the different masses of stellar halos is mostly the small things. And so just having a sense of how much light is in there, and maybe even looking at a slope, although that might be there, the theoretical predictions there are not clear if you would expect a difference in slope or not. But yeah, just looking at the amount of light that's in the outer halo is going to tell you about how many of the small things you would have, which is actually what is constraining the low mass stellar mass to halo mass relation.
I think Tavisha, and then do the last question.
Thanks, Tjitske. Very exciting. I wanted to ask you about the last slide that you showed on totally nerds on growing work. I'm wondering what implications does this have for sort of the Milky Way streams that we're seeing now? Could 3 streams that we have actually have been one event that's now broken up into 3? And then what would that mean for like the Milky Way's, what we understand about the merger history right now, or ongoing mergers and things like that? Would it change drastically, or yeah?
Okay, so I think there are a few things there. So one is, yes, I think there is actually cases where people have found individual streams and they now think that could be the same thing. So that is definitely happening, and it could well be more. The reason for that is this could be one of them. That actually the ejection of stars from globular clusters that get stripped from globular clusters goes more in bursts than we thought it did. And the orbital evolution in an evolving potential just accentuates small differences there. Another option is what we see in the stellar streams in the merger case is actually you can change the stellar streams in many different ways. You can move them from the inner parts to the outer halo. You can move them from the outer halo to the inner halo, completely changing their orbit. You can change the orbital plane, but you can also split them. And we have streams that fold double. We have streams where one part moves to a very large orbit with a very large epicenter, and the other part is actually on a nicely circular orbit in the inner halo. And so any of those interactions could cause that as well. And the Milky Way had some like more active merger history a bit longer ago. Like Sagittarius is one. the Gaia sausage Enceladus is another. The question is, will we still see streams that are that old? And I'm not completely sure about that answer. But yes, all of those could definitely make the same stream appear as different ones. So.
Cool. Last question.
Yeah, I'm just wondering, when you have this merger simulation, where you have this 1:6 ratio merger, do you simulate that just with the potential of the incoming thing, or does that actually perturb the potential of the Milky Way itself when you're simulating there? Because the Milky Way potential is also going to get super deformed from having that
Yes.
that thing there. So I'm thinking just like that's another confounding factor that I don't know if that was in there.
Absolutely. No, both of this is happening. This is live and body simulation. So we have the full reaction of the host galaxy halo. We also have the stripped component, stripped dark matter component of the satellite. That will leave a density or make small changes in the density distribution. So in many ways, that merging potential is non-spherical, it's non-smooth, and that changes how all these streams look.